Okay, so we are now starting to get quite close to the end with our lectures. So this lecture and Wednesday, and we'll have finished all of the course material. Okay, so then the next lectures after that will be, there'll be one lecture which looks at examples of this type for the things we're going to look at this week, and then it'll be revision. Okay, so what we're going to do this week is we're going to look at two practical examples which take the work we've done on rigid body dynamics and looks at it in a sort of context for aerospace engineering. So we're going to look at balancing this lecture, and then gyroscopes next lecture. Okay, then as I said, the lecture after that will have some examples of both of those types of practical situations. Okay, so with balancing, we're going to this is something that all rotating components have. So those of you that drive cars will know that when you take your car to have its tires fixed, they very often will have to balance the tires, and what that means is that they spin them at high speed, and they make sure that if there's any distribution of mass that isn't perfectly equalized all around the disc, okay, they add small lead weights, okay, to compensate. And what they're doing is they're balancing in terms of adding extra little bits of mass, okay, to stop any unwanted vibrations. Okay, because as we saw from our previous lectures, if you've got a slightly eccentric mass, okay, so you get a vibration. So for a rigid body component, if you have a small error in where the mass is centered, then you'll also get unwanted vibrations. Okay, so what we need to do is to analyze this using our framework that we've already worked out, is we need to think about the sort of framework we're going to use for our components, and we can keep thinking about our I, J and K coordinates. Okay, so we can think about I and J, but this time instead of K coming out of the page, I'm going to draw K. Okay, we're still going to think about things in planes, okay, and angles along the K-axis. So the IJ plane is going to be, we're going to use that as our reference plane, and then K is going to just be for angles. Okay, but this, we now have to think a little bit more in 3 dimensions, okay, for these problems. Okay, so, and if we just think about a vector along the J-axis, okay, so, and that's going to a point. So if we have a mass on the J-axis at point B, and we call the origin point A, the distance there, call this RBA, and then we'll have a tangential vector if it's rotating around the K-axis in the positive omega direction. Okay, so if we have if you imagine we have a mass at point B, okay, and it's going to rotate around in the IJ plane, okay, and it's got a distance from the origin R, B relative to A. Okay, so this velocity up here is going to be the velocity of B relative to A. Okay, and this is going to be equal to omega crossed with R, B relative to A. So in this case we have V, B relative to A is equal to omega crossed with R. And of course we consider omega to also be the vector of along this K direction, don't we? So if we have omega with a line underneath it, it means the vector, which is the rotation around the K-axis. Okay, so it's the angular velocity and what I should have perhaps said at the start is that points A and B we're actually assuming are on a rigid body. So if we have some rigid body like this, we have A and B, Okay, and B represents the eccentricity from the true center of mass. Okay, so what that means is it's the error, if you like, in terms of the mass distribution. It means the mass is not distributed in a way that's sort of central. So we're going to get an out of balance effect when we start to rotate this component. And of course, we've been through the derivations now to work out what the accelerations are for a mass. If we draw the same framework, draw the IJ planes like this, with K coming out this direction, and we have our mass at point B. So now we have worked out that there's components to the acceleration, okay, and in some of the tutorial sheet solutions, you'll see this notation. Okay, so if this is the acceleration of B with respect to A, you sometimes see either a subscript or a brackets and a subscript with N, meaning normal. Okay, so that means pointing back in or out. Okay, so a subscript N means the normal part of the acceleration. Okay, and so in this case, that would be omega crossed with omega crossed with R. And so by that logic, this component of the acceleration A, B with respect to A is the subscript T, or tangential part of the acceleration. Okay, so we sometimes talk about components as normal and tangential. And the acceleration that's tangential is equal to alpha crossed with R, where alpha is the angular acceleration of the rotating component. Okay, so that's our kind of starting point. We're going to think about a mass rotating in a plane, and that mass is representing the distribution of the mass on the rigid body, okay, which is eccentric to its true center. Okay, so it's an out of balance effect. So for balancing, typically we consider a shaft with an out of balance mass. Okay, so what we're going to do, just do a sketch of that. Okay, so almost all applications, if you think about gas turbines, for example, they have multiple discs or sets of fan blades on a shaft. Okay, so what we end up doing is we start with one thing in the plane. Okay, but in a minute we're going to expand that to multiple things in the plane, and so this is going to be like analogous to the k-axis, the shaft. And then there's going to be a series of planes, which will be the IJ type axes. Okay, so when we draw a mass that's rotating around the shaft, you have to imagine it's rotating in a specific plane, okay, which would be like the IJ plane. So what we draw normally is a distance. Well, I won't give it a vector at the moment, and a mass, and a angular velocity of the shaft. Okay, so these things on the left are all scalar quantities, okay, and you'll be glad to hear that most of the time for this analysis we'll just work with scalar quantities, okay, because that's the classical analysis. But of course, because we've got the IJK framework, if we want to, we can go back into that framework as and when we need to. Okay, so if we've just got a constant acceleration, a constant angular velocity, so rotation, which is what normally most things are, most problems we're considering would just be that, then if we go back to our acceleration diagram, we won't be accelerating at the tangential direction, okay, if we've got a constant rotational speed. There'll just be a normal type of angular acceleration, okay. Okay, so the acceleration is just that one component, okay, that's the normal component. So if we want to work out what that really is, okay, we have to do these cross products, so let's just quickly think about what they are to convince ourselves we know what's going on. Okay, so the cross product of the way we've set it up would be something like this, wouldn't it? Because the omega vector is just the scalar version of omega times k. Okay, so the other bits are 0. And the r vector is always going to be in the plane of I and j. Okay, so there's just an I component and a j component, and then the third component is 0 because there is no r bit coming out of the plane. So we would have something like this. Okay, and if we work out what we get there, we end up with minus r2 omega I plus r1 omega j. So then if we want to work out the next cross product, we have to cross omega with this bit that we've just got. Okay, so that equals something like this. So what we get is first vector is the same, and the next vector is something like this. And if you multiply that out, what you'll find is you get minus omega squared times the original r vector. Okay, so if you want, as an exercise, you can try and convince yourself that that's true, but actually you get something relatively simple coming out. So that's useful, so that we know that the acceleration is a relatively simple quantity if the rotation is constant. Okay, so this is the acceleration. So then the magnitude of the force applied to the rotor is, so the size of the force vector is equal to m omega squared times the size of the r vector. Okay, so we're using absolute values here rather than putting in the signs, just to tell us what the size of the force is, because this thing is rotating around the whole time. Okay, so the direction of the force is going to be continually changing. Okay, so it's more useful just to think about the size of it, how big is the force that's being applied. Okay, and so for a single eccentric mass, like we've just drawn, this is kind of where we get to. Okay, we can't do anything about it, it's there. Okay, and this is the force that it's applying to the shaft. So the next stage is we move to multiple masses in the same plane. Okay, so that's the next level of complexity. So again, we'd have the shaft just as we drew it before, with bearings at each end. Like this. It's rotating at constant speed omega. We've got original mass m, distance r from the higher. I think if you look at the line above, because of the way the cross product works, it ends up swapping them around. So you end up with, if you look at the line above, it's underlined. It says minus r2 omega I. So that's what goes into the next matrix, and then r1 omega j. There should be a line under the j. Do you see what I mean here? So the I component is this, and the j component is that. Comes out of the first. In the cross product, everything gets changed around, doesn't it? Because of the way this is multiplied. Yeah. You mean? I think if you work it out, if you just try it, you'll find it works out. Okay, it's just a bit non-intuitive. So, if we've got this is our previous situation, and then we may, in the same plane, we may have another mass, which I'll call capital M, distance capital R from the shaft. Okay, so these are both in the same plane. Okay, if we, in the really simple case, if we made them have the same angle, so they were directly opposite each other. Okay, so if we had a very simple case, if we had R and M, and we made this exactly opposite each other, okay, then I think most people would see that you could balance that by just having M omega squared R plus M omega squared big R equals 0. Okay, so you're essentially taking the forces that each of them produces and saying they've got to add up to be 0, so they're cancelling each other out, aren't they? So So we can generalize this idea of adding things together. Okay. So for several out of balance masses in the same plane, balance can be achieved by using the vector sum. And the way we do that is we add up all the components and we call what is equal to the residual. Okay, so we sum up. So the ith, okay, so this is I without an underline, this is the index I. So the ith mass times omega squared times the ith r vector equals a residual mass times omega squared times a residual vector, capital R. Okay, so omega is a constant, isn't it? So we can divide that out from both sides, because this is the case for constant shaft rotational speed. So actually the sum of the ith mass times the ith vector is equal to some residual mass times a residual vector. Okay? And what you'll see when we do this in 2 lectures time is that we do it in a systematic way by writing down a table. Okay, you have a list of all the masses, and then you start working out all the different components, and you tabulate the results. And so it's an easier way to try and deal with these problems. So that's multiple masses in a plane, all in the same plane. But now let's think about if we have masses that aren't in the same plane. We've got several different planes on the shaft. So this is out of balance in multiple planes. So same setup as before, shaft with constant angular velocity omega. But now we're going to have masses which are in different planes offset along the distance along the shaft. Okay, so in this case we're going to have small m, small r, and big M, big R, like this, and they are separated by a distance d. So this can be statically balanced. Okay, just by using the process we've already outlined, by doing the sum of the components. Okay. But as I'm sure you can see during the rotation, okay, there's also going to be moments applied, okay, to this shaft, because essentially in each plane a force is being applied on the shaft, isn't it? So each component will apply its own moment effect. And the terminology that people use is they say that it can be statically balanced by just adding up using the vector sum, okay, but it's dynamically out of balance because of these moments that happen, okay. And for the dynamic balance, we need that the sum of the masses times the R values times the D values is equal to 0. Okay, so we can add it up and it'll be equal to a residual initially, won't it, on the right hand side? And then quite often what the problem asks is a bit like when you have your car wheels repaired. You know, what do we need to do to get this right hand to be 0? Okay, so that what we're aiming for is for the right hand side to be 0 in both cases actually. So we want the residual to be 0 after we've balanced the system. So if we have a think about it, the sort of final level of complexity so in the final level of complexity we've got things in different planes at different angles. Okay, we could have multiple masses in one plane, other masses in another plane. Okay, so that's the sort of final bringing everything together. So we have our shaft like this. I'll just draw two, but we'll have something along this kind of lines. So I've only drawn one mass in each plane, but it's possible to have other masses in each plane as well. So these are the important quantities. Okay, you need to know what the mass, you need to know what the distance from the shaft is, r. You need to know at what angle these are. Yeah. 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 So in this one I drew them in the same angle, didn't I? They're equal and opposite angle to each other. Okay, so this is the... So, like I say, we're going to do the tabulation in another lecture, okay? But what we're going to do now is set up the scenarios that you're typically asked in these types of questions, so that you start to get an understanding of how the tabulation can be applied. So the first scenario is, as we've drawn it, it's a shaft with bearings. And typically you can be asked to find the bearing forces. So the normal approach is to take moments about one of the bearings, so once you've decomposed using the tabulation what's happening in each plane, you can kind of treat this shaft like a beam, if you like, that's having loads applied to it. You can take moments around if you take moments around one of the unknown bearing forces, means it's out of the moment calculation, isn't it? And then you proceed as you would have done with your other mechanics sort of problems. So maybe we should say, above this, we could say use tabulation to solve static and dynamic balance. Okay, so you tend to do that. The first thing you do is you tend to do the tabulation, and then you would then apply it to the bearing forces. So, second scenario that you can come across is scenario 2. A shaft with some unknown masses Okay, so quite often you're given a reduced set of information. So if you look in some of the past papers, sometimes what it does is it gives you a table for the tabulation, and it just fills in some of the quantities, and there's lots of blanks, so you have to work out what the other things are. Sometimes it doesn't give you the table, it just lists them in the question. It just says there's the shaft with 3 planes and the following information, and then you have to draw up the table and kind of put in the information yourself. Okay, but sometimes information about the masses is not there, and they're very often asking you to work out what mass you could put there that would balance the system. Okay, so that's a typical question. Okay, so in that case, you don't need to really worry about the bearings at all. You can just treat it as an independent system. If you take moments about the plane where the masses are not known, okay, that's the same trick as we just talked about, isn't it? Okay, because you don't know what's happening there, you take moments there. Okay, then that eliminates that from that moment calculation, and you can solve the problem normally. So in both cases, it's possible to find equivalent masses and radius in each plane. Okay, so you can either treat each plane as a if you've got multiple masses, you can find just an equivalent one mass and distance, or you can use it to find the missing mass that needs to be added. Okay. Okay, so next time we're going to do gyroscopes, and then next week we'll do the examples. Okay, I'll see you on Wednesday.